webcams, guys. So for the panel, it's similar to the session we had in the morning where the audience should feel free to ask general questions on multi-agent behavior to everyone on the panel, and then we can just everyone on the panel can comment and we can discuss on these questions. So I'll give the audience a few seconds to submit questions either on Zoom or you can unmute and then just ask.
Maybe I can kick off with a question.
Okay, thanks. Hey,
Patrick, how's it going?
Hey, Yusung. Well, good, Matt.
Thanks for participating and for your talk. I wanted to probe deeper on a point you made about deep neural networks not being interpretable enough. I think this point was raised across a few different contexts. Can you just give us a sense of the frustration you get for making deep learning interpretable for the domain?
So that's a really good question, Yusung. So I don't think it's the fact that it's interpretable, the lack of interpretability. I think it is using deep learning. It is more from our perspective, not utilizing the things that work. So feature engineering. So just say for event detection in basketball, if you're good at feature engineering, if you're a reasonable data engineer, you can get everything that you need, right? So if you have a right interface, you can craft features reasonably well. You go through a couple of rounds of active learning, you can get what you need. Now, also that gives you the optionality. So when we work with customers and clients, they just don't want the prediction. They want additional qualifiers on top of that. So it could be, I use an example, sorry if it's very precise to basketball, such as an off-ball screen. So it's not good enough just to say, well, an off-ball screen happened between T1 and T2. We want to know the agents involved. Sometimes they do want to know the position. Sometimes they do want to know the velocity and acceleration of that. And sometimes they do want to have it interpretable, such as they want to have thresholds. They want to make it interactive. And so I think so obviously you can use a feed-forward deep neural network. However, you do want to be able to interact with the features and set those thresholds. So I think often, and these are discussions that happen within my group, we can go fully end-to-end, just put in the raw positions, go fully end-to-end and have that output. That's great, it can work really well, it's really efficient. However, it doesn't give you the optionality of everything that you want. Yeah, so I think, obviously deep learning works and it works really well for vision data, speech data, text data, but sometimes when we have discrete data, just simple, because basically when we're doing feature engineering, we're linearizing the data and we're getting some benefit there. So I think my point is just more, let's not throw deep learning at everything. There are classical techniques that we can use. And really when we're dealing with customers, I think Raquel said, like getting stuff in production, making it interpretable so we can debug it and explain it to our customers. That's really important too. Yeah, does that make sense?
Yeah, okay. So my quick follow-up question, then I'll open up for others to ask questions or contribute to the discussion, is what do you see as a hybrid solution that gets the best of both worlds? Like the flexibility of deep learning coupled with all the regularities and the structure and the interpretability of, feature engineering?
Yeah, I think it's more around interfaces. Being able to have a question answering tool where you can interact with the data and ask the questions that you want. And really, that'll enable you to go end to end and you actually know what the specifications of the output are. So I think often when we have a prediction task, it's just like, well, I just want to optimize for that prediction task and then you can solve that. However, when you're going end to end and debugging, you want to be able to interact and kind of get that output where you can explain it. So I do think that's a hybrid, but it's more around getting the specifications where you have the telemetry or you have the ability to interact with your system so you can get the right answers out. And so it's a very, very useful way to debug and just to get an insight of what's happening. But I think that's really the key. I don't think it's one or the other. I just think it's through using interactive design and being able to, it's kind of like a multimeter. Back to electrical engineering days, we want to put a sensor on so we can just get the measurement out. I think sometimes we haven't got the ability to do that because it's too end to end.
I wanted to maybe let James comment on that, those points in the context of autonomous vehicles if he wants.
I'd love to, but I joined after the question was asked, I think.
The question was about interpretability and end-to-end deep learning, and how sometimes feature engineering with linear models is sometimes more preferable to the customers because it's more interpretable, more structured, and how does one potentially get hybrid approaches to get the best of both worlds?
Yeah, I think I totally agree with that. I personally love to see these approaches that are more interpretable than pure end-to-end methods. I think they have a lot of benefits. But yeah, sometimes maybe not quite as much performance as if you had optimized end-to-end for one thing. I think Raquel, she's not here, is she? But I mean, Raquel's group has done a great job of producing these methods that are end-to-end, but still have interpretable intermediate stages. So you know, I would give her credit for that. Yeah, I do think it's a worthwhile thing. And personally, when reading a paper, I really love to see the simple, interpretable, even hand feature engineered things first, just to get an intuition for the problem and the data itself before turning the crank on deep learning.
Okay, I guess since we have people from sports analytics, self-driving, and animal behavior like Ben here, one question for all of you guys is like, what timescales are relevant when you look at behavior in your domain, and how do you know when you've included enough past information to predict the future or quantify behavior accurately?
Yeah, I might answer that. That's a very good question, Jennifer. I'll give my perspective because I think Yisong, you asked that question about taxonomy. I think especially for sports, it does exist at different scales. So we have it at the possession level. So we have that as our unit of analysis, and then we can roll that up into multiple possessions. And when you're thinking about different techniques, so for sport, you can't really predict longer than a possession. Within a possession, you can do some really nice things. And so I think having that global taxonomy or that kind of temporal representation or that representation of scales is really important, because you can think of it more as the macro and the micro. And I saw a really good talk last week by Tony Jabara at the AI Summit, where they're trying to optimize a recommendation system for lifelong learning. And so I think that's at that scale where you can optimize across that scale. And so again, this is where I think having some intuition, setting the bones of the story or that scale, where you can try to optimize across, the micro or the macro or some hybrid approach there. So that's where I do think you need to kind of set the bones of the story to enable that type of analysis to optimize for those prediction tasks. But yeah, I'd love to hear what James says in terms of autonomous vehicles. Obviously you don't want to hit someone, but obviously you want to look at fatigue of the car. There are other things, or it'd be interesting to get your viewpoint on that.
I haven't thought as much about really long time horizon forecasting in autonomous vehicles, but yeah, you're right. The immediate concern is certainly the next few seconds where you need a correct prediction, because 3 seconds, it might take you that long to stop, right? And so that's certainly a critical time horizon for self-driving. But you could imagine that there are driving scenarios that play out on the scale of almost a minute. This person needs to get across the street and there's a traffic jam and this car is backing up and this other car needs to clear first. Like, you could imagine all these complicated interactions that could take a while to unfold. And you would want to understand intent on the scale of maybe even minute timelines. But I'm not thinking of much that would go on beyond that. I mean, forecasting beyond that, you would just, you want to know, like, what does the traffic pattern look like at 4 p.m. on a Sunday or something? I guess that's a thing as well.
So do you mind me asking that, James? So just say, like, obviously for autonomous vehicle, it needs the best availability is, the best ability is availability. If a sensor breaks on the car, do you factor that into autonomous vehicles? It's kind of similar in sports like injury. We need to optimize so we don't get that player or that agent injured. Obviously, the first thing with autonomous vehicles, you don't want someone to get hit by the car. But do you think that's kind of like a longer term research problem where you want to optimize so the car can stay on the road, it doesn't break down?
That's a good question. Yeah, I haven't given much thought to that. I think, right now, if faults are detected, I would imagine for Argo or any competitor, that they would just pull over safely and deal with it. not try to limp along too much. But that's an interesting idea about trying to understand how your own capabilities might degrade, or how the capabilities of others around you might degrade, I suppose, as well. It would certainly, realize that the car next to you has not scraped the snow off their windshield, so their driving might be a little different, something like that. Yeah, it's an interesting idea.
Ben, did you have anything you'd like to add from your work on bees, for example?
Well, I mean, there's also simply the problem of what can your models learn, right? If you look at simple LSTM models, for example, you can put unlimited amounts of historical data in there, but in practice, I think there's been a couple of papers which have shown that, like, past the limit of like 100 or 200 steps, these models will fail to utilize historical data. And then, of course, there's also the problem of, I mean, it kind of depends on the setting you have, right? Like, if you have a lot of training data, you can use more fancy architectures like transformers, which might be able to use this, but then, of course, you need a lot of training data. So for our honeybee data, the behaviors we do have are kind of simple to detect, at least those that we did automatically detect as of yet. So we didn't have to use a lot of historical data. So yeah, I guess my answer would be it depends very, very strongly on the problem you're trying to solve and on all the constraints you do have in terms of amount of available data and how expensive it is to acquire this data.
Thank you. And we are actually a little bit over time for our discussion, so thank you guys for staying after to do the discussion. We would love to have a longer panel, for example, for future years. So Anne, did you want to say a few words?
With that, we're going to wrap up the workshop since we've run a little bit over. But we thank all of the speakers for coming and joining us and sharing their various perspectives. Also, thanks to Ben and to the team at Upwell Research for their contribution during the challenge. And thank you all for joining us.